We can use sort of a familiar reaction format or reaction to kind of notation to write this protein ligand association reaction. Okay, so we can write P plus L going to P sort of dot L here. So this is, P is representing the protein, L is representing the ligand, and this notation here is indicative of the complex, okay? Or they're now bound together. And we could write an equilibrium constant for the forward reaction. K would be equal to, what would go on the top? Concentration of the complex, because it's the product, and then the bottom we have the concentration of, again, these are unbound or free protein and ligand. So these are the concentrations of free or unbound protein and ligand. We call this the association constant, with a capital A down here. This is distinct from K sub lower, or yes, K sub like a lowercase a, which was our acid dissociation constant. But since the class is not cumulative, your new equation sheet, K sub lowercase a for acid dissociation, we won't bring that back, so it doesn't matter as long as you can now orient yourself to this new notation. Okay, and then we also had a relationship for any equilibrium constant to standard state free energy change. Okay, and we are looking at change in free energy, delta G, at standard state. This was equal to negative RT, the natural log of KEQ. So we can write this delta G for our binding reaction, binding or association, whatever you want to call this, is negative RT, the natural log of K sub A. So this is the change in free energy when 1 mole of protein binds 1 mole of ligand under standard conditions. What were our other standard conditions? Some sort of specified temp, could be 298 Kelvin, or now that we're going to start talking about body temp, we'll probably start using 310, but it'll have to be given to you. Pressure is going to be 1 atmosphere, and pH, 7, 7.4, something in that area, such that we're also going to have, what was our standard state concentration for water? 55 molar, and then that means if we're at 7 pH, what's going on with our hydrogen protons? If we're in a buffered system, what was the concentration for that? 10 to the negative 7th molar. Perfect. Okay, and so you might, like I said, we could call this binding free energy change. Free energy change, standard state free energy change of binding, any of these words will indicate what I'm going for. Okay. Delta G of binding is a measure of affinity. Where basically the more negative this number, the stronger or more favorable the binding. What that means is it would take energy input to pull these two things apart. Okay? And the lower that number, the more energy you have to get in to pull them apart. Okay, so we can also write the reverse reaction. This would be our complex dissociating or unbinding into free protein and free ligand. And the equilibrium constant for this is 1 over K sub A, 1 over our association constant. Or we can write it as concentration of free protein, concentration of free ligand over the complex. So this is our dissociation constant. And it is also equal to 1 over K sub A. So now we can write delta G of unbinding as equal to negative RT, the natural log of KD. If I'm interested in the delta G of binding in terms of KD, what happens? Right? So because it's the natural log, my sign is going to flip. I can plug in, 1 over K sub A into here, and it will be the positive version. So you're going to have, this is equal to, this would be equal to positive RT, the natural log of 1 over K sub A. No, it's not. Binding. Okay, the sign is flipping when I go in the reverse direction. And this is where, as you can see, even I am messing it up. Pay attention to what your subscript is asking for. So recall that technically K sub D is actually given by the concentration of protein over the standard state concentration of protein times the concentration of ligand and the standard state concentration of ligand. And this is all over the complex and the standard state concentration of complex. And then we let all of these be equal to 1 molar for standard state. And so we've been dropping all these bottom terms for ease. So the actual units on this we said were dimensionless. Okay? This would be molar over molar times molar over molar divided by molar for molar. And this would be dimensionless. But biochemists like to put units on K sub D, okay, so that they can have an easy way to relatively compare these things and determine affinity. So biochemists, first of all, they think everything in K sub D as opposed to K sub A. And they let this be, we have P L over our complex. This would be molar over molar divided by molar. They let these drop out and they let this have units of molar. Okay. It's a relative scale of affinity. What would be the units of K sub A? One over molar or molar to the -1. So they use K sub D simply because it's easier to have molar than 1 over molar as your unit. Okay. Molar is just easier. And then what you can think about is when K sub D is in the picomolar to nanomolar range. So when we're in 10 to the -12th, sort of 10 to the -9th. The way to think about this is that your free ligand concentration will be very low. K sub D is very small. Okay. When K sub D is very small, this bottom term is very big. Everything is complexed. Okay? And so you have very tight binding. You have very high affinity. And so again, it's a little bit counterintuitive to think this way, but the smaller this dissociation number, the stronger the binding is because they don't want to dissociate. And when you are in the micromolar to millimolar range, sort of 10 to the -6 to 10 to the -3rd, then you have a slightly higher free ligand concentration. It's a little bit higher, K sub D is higher, and this is sort of weaker binding, lower affinity. Okay, and so these are all less than 1, of course, because we have more bound together protein and ligand than we do free concentration. Another way to think about this is that you need less ligand. For high affinity, sort of tight binding cases, you need less ligand in order to see appreciable binding and to get eventual saturation. So it's sort of, and we'll get to this, these concentrations, these K sub Ds also represent concentrations of sort of total ligand you need to start to measure binding and also like saturate. Okay? So something that has really high affinity and really tight binding will saturate at a much lower concentration than something else. If it's not a very favorable binding interaction, you'll have to put in more and more and more and more in order to get all of the protein to bind to it. Okay? And another thing to think about is that the concentration of protein here, such as in the body, isn't really changing. So there's some sort of regulation to this. I mean, you might have periodic times of things being upregulated or downregulated depending, but concentration of protein isn't changing. So you're interested, especially with maybe drug design, settling on what's the concentration of drug I want to deliver to make something happen. Or in experiments in the lab, you also generally would maybe have control over protein concentration. Okay? You could set that and then vary your ligand. Any questions? Okay. Yes. So the way to sort of think about a low KD as being sort of tighter binding or higher affinity is that you need less ligand in order to start to get the binding to happen. Yep. And you'll saturate all the receptors sooner. I forgot to bring